Hello everyone. In the previous video we have learnt about the congruent circles, its properties and theorems and the proofs of them. In this video we will be learning about the different angles subtended by an arc in the circle. The first property or the theorem comes: the angle subtended by an arc at the center of a circle is twice the angle subtended by the same arc at any point of the remaining circumference. What we do? First of all, we draw the diagram. The diagram is here. This is a circle with radius r and center O. An arc AB is given here. The angle subtended by this arc at the center is angle AOB. And in the remaining circumference, we have taken a point P. At the point P, the angle subtended by the same arc is angle APB. So what is given to us? A circle COR in which arc AB subtends angle AOB at the center and angle APB at the point P of the remaining circumference. What we have to prove? To prove that this angle AOB is twice angle APB. This is what we have written here to prove. The construction. There is a construction required: join PO and produce it to a point Q. So we write here join PO and produce to Q. Now, in this particular theorem, there may be three different cases. Like the first case is here, in which we have the arc AB is a minor arc. The second case may be when arc AB is a semicircle. And the third case may be when arc AB is a major arc. We will be discussing now the first one, when the arc AB is minor arc. So we are taking the first case here when arc AB is a minor arc. Going to the proof of this part, what we find? If we go for triangle AOP, what we find? This angle and this angle are equal because this OP and OA are equal. They are the radius of the same circle. And we know that the angles opposite to the equal sides are equal in a triangle. So applying that, we write in triangle AOP, OA is equal to OP, that is equal to R, the radii of the same circle. This implies that angle OAP is equal to angle OPA, that is angles opposite to equal sides. This we have written as angle 2. It means both are same as angle 2 or not. Now we also know that exterior angle of a triangle is equal to the sum of opposite interior angles, and here angle 1, that is angle AOQ, is exterior angle of the same triangle. Angle AOQ, which we have written as angle 1, is an exterior angle of triangle AOP, and therefore we can write that angle 1 is equal to angle 2 plus angle OAP, and this is also angle 2, so this is angle 2 plus angle 2, we can write twice of angle 2. Similarly, in triangle OBP, we have written the exterior angle as angle 4 and this is angle 3. This angle and this angle are equal. So we will get angle 4 is twice of angle 3. We can prove angle 4 is equal to twice of angle 3. If we add these two, angle 1 plus angle 4 will be equal to what? Twice of angle 2 plus twice of angle 3. If we take 2 common, this is angle 2 plus angle 3. And we know that angle 1 plus angle 4 is angle AOB. And angle 2 plus angle 3 is angle APB. So this is twice of angle APB, and that's what we had to prove here. So in a minor arc, we find the angle subtended at the center by that is twice the angle at any point of the remaining circumference. In the second case, we find that arc AB is a semicircle. So AB is a diameter and this arc AB is a semicircle. We have taken the same angles here also, 1, 2, 3, 4, and similar case we can take in this triangle OA equal to OP. This angle will be equal to this, and angle 1 will be twice of angle 2. In this triangle also OB is equal to OP, and so angle 3 and this angle are equal to each other, and we can prove that angle 4 is twice of angle 3, and adding that we get angle 1 plus angle 4 is equal to twice of angle 2 plus angle 3. And hence we can prove that angle AOB, it may be a straight angle, is equal to twice of angle APB. So in second case, when this is a semicircle also, we can prove that the angle at the center is twice the angle at the remaining circumference. In third case, we have taken that AB is a major arc. Angles are taken same 1, 2, 3, 4. And the same way we can go in this triangle and prove that angle 1 is twice of angle 2, and here angle 4 is equal to twice of angle 3. When we add them, adding them we get angle 1 plus angle 4 is equal to twice of angle 2 plus twice of angle 3. Taking 2 common, this is 2 into angle 2 plus angle 3. Here we find that 1 and 4 are having a sum that is reflex angle AOB. So we write here reflex angle AOB is equal to twice of angle APB. So in all the 3 cases we are finding, let it be a semicircle, let it be a minor arc, let it be a major arc, the angle subtended at the center is twice the angle at the remaining circumference at any point. The next theorem is angles in the same segment are equal. For this we draw the diagram. A circle with center O and radius R. AB is a coordinate, and the angles in this segment are formed by this chord AB, that is angle APB and angle AQB. So these are the angles in the same segment. We have to prove that these two angles are equal. So we write, given a circle COR in which angle APB and angle AQB lie in same segment, that is by chord AB. To prove angle APB is equal to angle AQB. Now you can think what construction we should do. We can subtend an angle AOB by the same chord AB at the center. So we write the construction, join OA and OB. So joining these we get an angle AOB at the center. Now the proof. In the proof we will quote that theorem which we have learnt just now, that we know that the angle subtended by an arc at the center is twice the angle subtended by it in the remaining circumference. So what we can write from this now? Here we are finding that this angle at the center and these are the angles in the segment. So we can write therefore angle AOB is equal to twice of angle APB. which implies that angle APB is half of angle AOB. This we can write as 1. Also we get angle AOB is twice of angle AQB, by which we get angle AQB is equal to half of angle AOB. This we can write as 2. What we get from 1 and 2? Both are half of AOB. Will they be equal? Yeah. So we can write therefore from 1 and 2 angle APB is equal to angle AQB. That's what we have to prove. So we can write hence proved. So like this we can prove that the angles in the same segment are equal. Next theorem we have that angle in a semicircle is a right angle or 90 degree. For this we draw a diagram. If we have a circle with center O and AB is diameter, we know that diameter divides the circle in two semicircles. So this is a semicircle and angle APB is the angle in the semicircle at any point P. So what we write given? Given is a circle COR in which AB is a diameter and angle APB is the angle in semicircle. To prove that angle APB is 90 degree, or we say right angle. There is no construction required. We go for the proof and then we quote the theorem which we have learnt before this. That is, we know that the angle subtended by an arc at the center is twice the angle subtended by it at the remaining circumference. So here we can say that angle AOB is twice of angle APB. This implies that angle APB is half of angle AOB. And we know that angle AOB is a straight angle. That is 180 degree. So we can write this implies that angle APB is equal to half of angle of 180 degree. We can write since angle AOB is straight angle. And half of 180 means this is 90 degree, and that's what we have to prove. The converse of this theorem states that if there is an arc which subtends an angle of 90 degree or a right angle in the alternate segment, then the arc is a semicircle. For this we draw a diagram in which we have been given an arc AB which is subtending an angle APB that is equal to 90 degree in the alternate segment. So what is given? An arc AB which subtends angle APB equal to 90 degree in the alternate segment. What we have to prove? To prove that arc AB is a semicircle. There is no construction required, so we go to the proof directly. And we quote the theorem that we know that the angle subtended by an arc at the center is twice the angle subtended by the same arc in the alternate segment or in the remaining part of the circumference. Therefore, angle AOB, which is at the center by this arc, will be twice of this angle APB or not? And APB is 90, so this will be 2 into 90, or we can say 180 degree. And if angle AOB is 180 degree, it means we can say that AB is a straight line. The diameter, that will be the diameter of the circle. And if it is the diameter, this implies that arc AB is a semicircle. This is the way we can prove this particular theorem. The next theorem is that if we have a line segment joining any 2 points, subtending equal angles and any 2 points on the same side of it, then all these 4 points are concyclic. It means they lie on the circumference of the same circle, or we simply say that they lie on the same circle. The diagram is here. We have a line segment AB. C and D are 2 points on the same side of it, and it is subtending equal angles at these 2 points C and D. So what is given? A line segment AB, C and D are other 2 points on the same side of AB such that angle ACB is equal to angle ADB. If we name them as 1 and 2, we can say this implies that angle 1 is equal to angle 2. To prove A, B, C and D are concyclic points, or we say they lie on the same circle. There is a construction. See, we can draw any circle passing through any 3 non-collinear points. So we can draw a circle passing through points A, B and C. Suppose the circle does not pass through D. What we find, there may be 2 cases. The first case is that D lies outside the circle. Second case, it may be that D lies inside the circle. Then what we do? In this, suppose it is intersecting the circle at E, join BE. In this case, we produce AD, and suppose produced AD meets the circle at E, then join BE. So we have written the construction here. Draw a circle through points A, B and C. There may be 2 cases. Number 1, D lies outside the circle. Second, D lies inside the circle. These are the first case and second case, both the cases. Then we write, let AD intersect the circle at E in first case, and in second case, AD produced at E. Now we come to the proof of it. In proof, we will quote the theorem that we know that angles in the same segment are equal. So we write here, we know that angles in the same segment are equal. So can we say that angle 1 and 3 will be equal to both the cases? Therefore, angle 1 is equal to angle 3. But given that angle 1 is equal to angle 2, this is given to us that these 2 angles are equal. What we find here? From these 2 we can get that angle 2 and 3 are equal. This implies that angle 2 is equal to angle 3. But what we see? In the first case, angle 3 is the exterior angle of this triangle BDE. In the second case, we find angle 2 is the exterior angle of this triangle BDE. And we know that exterior angle can never be equal to one of the opposite interior angle. It means what? This is possible only when D lies at E. It means D and E coincide. This is possible only if D and E coincide. Why? Since exterior angle of a triangle is not equal to the opposite interior angles. And if they coincide, then all these 4 points lie on the same circle. Therefore, A, B, C and D lie on the same circle, or we say they are concyclic points, hence proved. So this is the way we can prove this particular theorem also. In the next video, we will be learning about cyclic quadrilateral and its properties or theorems. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.